In this lesson, we're going to explore the energy changes that occur during a chemical reaction, taking a look at thermodynamics and kinetics. Thermodynamics and kinetics are the study and measure of the two primary energy changes that occur during a reaction. When studying these energy changes, it's often convenient to represent them graphically and semi-quantitatively. A reaction coordinate diagram, or free energy diagram, shows how the energy of the reaction changes while progressing from reactants to products. Free energy diagrams are actually really simple, but can be a challenge to understand at first. A chemical reaction is really just the transformation of reactants into products. That transformation will typically involve breaking existing bonds and forming new bonds. And it's important to remember that when a bond is made or broken, it's not like flipping a light switch. It's not just on or off. It's more like a dimmer switch. When a bond forms and two atoms get closer together in space, their orbitals will start to overlap, and as that overlap occurs, the energy of the system will go down. When a bond breaks, the atoms distance themselves, the amount of orbital overlap decreases, and the energy goes up. A free energy diagram graphically depicts the energy changes that occur as bonds are gradually made and broken. So here I have a simple free energy diagram. You can see that on the left, we have our reactants, and on the far right, we have our products. So the horizontal axis is representing the progress of the reaction as the reactants transform into those products. And there are an infinite number of microscopic changes that occur during that process as bonds are forming and are being broken. The vertical axis represents the energy that's changing during those transformations. The vertical displacement represents the energy, with a higher placement representing a higher energy. So you can see that in this example, as the reactants start the reaction, the energy climbs up, reaches a high point, which is called the transition state, and then the energy falls back down to the products. The transition state is, by definition, the highest energy species formed during the reaction. And because it's so high in energy, it's transient. It only forms for a split second, and it typically involves both partially formed and partially broken bonds. Let's start by looking at thermodynamics. Thermodynamics is just the study of reaction equilibria. In other words, if you have a reaction going from reactants to products, and it's allowed to go backwards and forwards, how much product will form and how much reactant will be left. Thermodynamics is all about the energy change between the products and the reactants, known as the Gibbs free energy change, or delta G naught. The Gibbs free energy change can be calculated by subtracting the energy of the reactants from the energy of the products. Delta G naught can also be calculated from enthalpy and entropy in an equation you've probably seen in some other chemistry courses. Regardless, a more negative delta G naught results in more product formation at equilibrium. In other words, the more stable the products are relative to the reactants, the more products will form. So here I have two free energy diagrams depicting what are considered exergonic and endergonic reactions. In an exergonic reaction, we have a negative delta G naught. The products are more stable than the reactants. And that means that this reaction is going to create a lot of product at equilibrium. In an endergonic reaction, we have a positive delta G naught, and that means that the products are less stable or higher in energy than the reactants. A very endergonic reaction will form very little product at equilibrium and have a considerable amount of reactant left over. Kinetics is the study of reaction rates and involves the change in energy between the reactants and the transition state. That energy difference is called the Gibbs energy of activation, or delta G double dagger. Delta G double dagger can be calculated by subtracting the energy of the reactants from the energy of the transition state. Delta G double dagger can also be calculated from the enthalpy of activation and the entropy of activation. Regardless of how it's calculated, a lower delta G double dagger gives a faster reaction. In other words, the more stable the transition state is relative to the reactants, the faster the reaction will be. So here I have two free energy diagrams depicting a relatively fast and a relatively slow reaction. In the faster reaction, you can see that the energy difference between the reactants and the transition state is smaller than in the slower reaction. In these examples, the energies of the reactants happen to be the same, but the transition state energy in the slower reaction is much higher. Also note that there's really no correlation between whether a reaction is fast or slow and whether it is endergonic or exergonic. Here, these two reactions are both exergonic. Many of the reactions we study in organic chemistry actually progress through multiple fundamental steps. They're considered multi-step reactions. In a multi-step reaction, the initial reactants will undergo some transformation, going through a transition state leading to products. Those products then react further through another transition state to create new products. This process can then repeat, giving rise to multi-step reactions that can be 4, 5, 6, even 7 steps long. So here I have a free energy diagram of a two-step reaction. You can see that the initial reactants go up in energy as they react through a transition state and then down to a set of temporary products called intermediates. Intermediates are actually the products of one step that will then serve as reactants in a subsequent step. So here, these intermediates will now react further with each other, going through another transition state, leading to the final products in this case. We can see that in this reaction, the overall transformation is exergonic. You can see that the final products are lower in energy than the initial reactants. But we can also look at it step by step. We can see that the first step is actually endergonic. The products are actually higher in energy than the reactants. And then the second step is exergonic. Starting with the intermediates, which serve as the reactants in the second step, you can see that the products are much more stable. Each step of the reaction has its own transition state, and that means that each step has its own rate. In this case, you can see that the rate of the first step is actually quite slow relative to the rate of the second step. The free energy of activation in that first step is much larger than in the second step. The rate of the entire process is dictated by the slowest step in the reaction, which is called the rate-limiting step or rate-determining step. And in this example, you can see that the first step is the rate-limiting step. Understanding thermodynamics and kinetics is really important for predicting whether a reaction will actually work. A reaction will only make considerable amounts of products if the products are more stable than the reactants. In other words, it must be thermodynamically feasible. Similarly, if a reaction is extremely slow, it may be impractical to run, or side reactions could be faster, leading to unwanted byproducts. In other words, the reaction must be kinetically feasible.